Let's dive into the invisible architecture that really runs our entire world. We're talking about two things you use constantly without a second thought: the internet and the electrical grid. And here's the crazy part: they share a surprisingly similar history and an even more connected future. It seems like a weird question, right? I mean, one sends this steady flow of power and the other sends just a tiny burst of data. But believe it or not, deep down, the networks they rely on had to solve the exact same kinds of problems. And amazingly, they ended up with very similar solutions. Okay, so to really get where we are now, we have to start at the very beginning. Both of these massive networks, power and data, grew out of this one single philosophy: the idea of a dedicated line, a concept called circuit switching. I want you to picture an old-timey telephone operator, with a switchboard. When you wanted to call someone, she would literally take your line and plug it into the other person's line. And poof, you had one continuous, unbroken copper circuit just for your conversation. That's circuit switching in a nutshell: a private, dedicated road from point A to point B. And this quote right here just nails the problem. A dedicated line was fantastic for a long, continuous phone call. But for computer data, which is all short, intense bursts, it was just incredibly wasteful. You'd have this entire digital highway sitting empty most of the time, waiting for that next little burst of data. And here's where it gets really interesting. Our traditional power grid was built on the exact same model. You've got a huge, centralized power plant at one end, pushing electricity down a dedicated, one-way path all the way to your home. Just like the old phone network, it was all designed for a single direction, with a fixed capacity, all controlled from the center. So this massive wastefulness of circuit switching for data, well, it was just begging for a revolution in thinking. People started asking, instead of a private road for every single person, what if we could build a massive public highway that everyone could share at the same time? And this was the absolute genius of packet switching. Instead of one long continuous stream, your email or your video gets chopped up into these tiny little pieces called packets. You can think of each packet like a letter with a destination address stamped on it. They all get thrown out onto the same massive public network, each one finding its own best path, and then they're all put back together in the right order at the very end. And this didn't just stay an idea on a whiteboard. It was actually proposed way back in 1965 in the UK. By 1969, it was being used on the ARPANET. Fun fact, the very first message was supposed to be the word login, but the whole system crashed after just two letters LO. But hey, despite that little hiccup, by 1983, this became the very backbone of the internet we all know and use today. So yeah, this four-step process is the magic. Your data gets broken up, addressed, and then just sent out into the chaos of this huge shared network, only to be miraculously reassembled perfectly at the other end. And the efficiency is just incredible because the network is always being used. If you're not sending a packet in a given millisecond, you can bet someone else is. No more empty, wasted lines. So, okay, the internet figured out how to handle all this bursty, decentralized information. But what on earth does that have to do with the power grid? Well, it turns out the grid is now facing the exact same kind of challenge. And this is the central aha moment of this whole thing. The rise of renewable energy is forcing the old, one-way, centralized grid to become something much, much more like the internet, a dynamic, multi-directional, shared network. So why the big change? Well, because renewable energy is bursty, just like computer data was. The sun isn't always shining, right? The wind isn't always blowing, and now your neighbor's solar panels might be pushing power back onto the grid. The old one-way system simply cannot handle this kind of chaos. It just leads to instability, limited capacity, and a real risk of blackouts. The solution? It's called the smart grid. And it's basically the grid evolving to think like the internet. It uses all kinds of sensors, data, and communication to manage this incredibly complex, two-way flow of energy that's coming from millions of different sources, from giant wind farms all the way down to the solar panels on your own roof. Okay, so if the smart grid is the new internet for energy, what's acting as its router? The answer is artificial intelligence. As you can see here, different types of AI are managing the flow. Machine learning is busy predicting how much power we're all going to need. Deep learning is spotting problems before they can cause a blackout. And reinforcement learning is figuring out the absolute best time to store or release energy. AI is the brain that makes this complex new grid possible. But wait, the story doesn't end there. Because just as the power grid is learning from the internet's past, the internet itself is facing a brand new challenge. And the solution, believe it or not, lies in its own history. You see, the very same AI that's helping optimize our grid is creating an unbelievable amount of data traffic. I mean, training just one of these large AI models can mean moving petabytes of data, that's millions of gigabytes, between servers. And for these huge continuous flows of information, the old system of chopping up and reassembling billions of packets is actually starting to become inefficient all over again. So what's the solution? Well, it's a return to circuit switching, but with a seriously futuristic upgrade. It's called optical circuit switching. Instead of a copper wire, OCS uses tiny mirrors to create a dedicated, uninterrupted highway of pure light, connecting two points directly, at the speed of light, with almost zero delay. Now, here's the trade-off. As you can see, OCS is actually much slower to set up a connection in the first place. But once that path of light is established, man, it is incredibly fast and uses way less power. So it's not for your everyday web browsing, but it is absolutely perfect for the massive, sustained data transfers you need for things like training AI. So today, you'll find this tech in really specialized roles. It's connecting massive data centers for AI, it's powering supercomputers that need to move enormous data sets, and it's creating ultra-secure networks where a dedicated, untappable line of light gives you the ultimate in both security and speed. So what's the big takeaway here? It's that there is no single best way to do things. The design of our most critical networks is this constant cycle of evolution. We moved from dedicated circuits to shared packets to solve one big problem. And now, to solve a totally new problem, we're circling back to these ultra-fast, dedicated optical circuits. It's all about finding the right switch for the job. So we've seen how both the internet and the power grid have learned from each other, becoming more flexible, distributed, and way more intelligent. But as our needs become even more extreme, you just have to wonder, what comes next? What new challenge is right around the corner that will force us to invent the next great switch that powers our world?